Good morning. Many counting problems can be solved by finding the number of ways to arrange a specific number of distinct elements of a set of a particular size where the order of these elements matters. Many other counting problems can be solved by finding the number of ways to select particular elements from a set of a particular size where the order of these elements does not matter. For example, how many ways can we select 3 students from a group of 5 students to stand in line for a picture? How many different committees of 3 students can be formed from a group of 4 students? In this lecture, we will develop methods to answer questions such as these. Permutations. Example 1.1. In how many ways can we select 3 students from a group of 5 students to stand in line for a picture? Solution. First, note that the order in which we select the students matters. There are 5 ways to select the first student to stand at the start of the line. Once this student has been selected, there are 4 ways to select the second student in line. After the first and second students have been selected, there are 3 ways to select the third student in line. By the product rule, there are 5 times 4 times 3 equals 60 ways to select 3 students from a group of 5 students to stand in line for a picture. Example 1.2. In how many ways can we arrange all 5 of these students in a line for a picture? To arrange all 5 students in a line in picture, we select the first student in 5 ways, the second student in 4 ways, the third in 3 ways, the fourth in 2 ways, and the fifth in 1 way. Consequently, there are 5 times 4 times 3 times 1 equal 120 ways to arrange all 5 students in line for a picture. Definition. A permutation of a set of distinct objects is an ordered arrangement of these objects. An ordered arrangement of R elements of a set is called an R permutation. The number of R permutations of a set with n elements is denoted P of nR. We can find P of nR using the product rule. Example 2. Let S equal the set 1, 2, 3. The ordered arrangements of 3, 1, 2 is a permutation of S. The ordered arrangement 3, 2 is a 2 permutation of S. Theorem 1. If n is a positive integer and r is an integer with 1 less than or equal to r less than or equal to n, there are P of nr equal n times n minus 1 times n minus 2 all the way down to n minus r plus 1 R permutations of a set with n distinct elements. Corollary 1. If n and r are integers with 0 less than or equal to r less than or equal to n, then P of nr is equal to n factorial over n minus r factorial. Example 4. How many ways are there to select a first prize winner, a second prize winner, and a third prize winner from 100 different people who have entered the contest? Solution. Because it matters which person wins the prize, the number of ways to pick the 3 prize winners is the number of ordered selections of 3 elements from a set of 100 elements. That is, the number of 3 permutations from a set of 100 elements. Consequently, the answer is P of 103 is equal to 100 times 99 times 98, or 970,200. Example 7. How many permutations of the letters A, B, C, D, E, F, G, H contain the string ABC? Solution. Because the letters ABC must occur as a block, we can find the answer by finding the number of permutations of 6 objects, namely the block ABC and the individual letters D, E, F, G, and H. Because these 6 objects can occur in any order, there are 6 factorial equals 720 permutations of the letters A, B, C, D, E, F, G, in which ABC occurs as a block. Combinations. Example 8. How many different combinations of 3 students can be formed from a group of 4 students? To answer this question, we need only find the number of subsets with 3 elements from the set containing 4 students. We see that there are 4 such subsets, one for each of the 4 students, because choosing 4 students is the same as choosing one of the 4 students to leave out of the group. This means that there are 4 ways to choose the 3 students for the committee, where the order in which these students are chosen does not matter. Definition. An R combination of element of a set is an unordered selection of R elements from the set. Thus, an R combination is simply a subset with the subset of the set with R elements. The number of R combinations of a set of n distinct elements is denoted C of nr. Note that C and nr is denoted by n choose R and is called the binomial coefficient. Example 10. How many subsets of the set S equal A, B, C, D are there that have only 2 elements? Since the order is not important, we find C of 4, 2 equals 6, consisting of the sets A, B, AC, AD, BC, BD, and CD. Theorem 2. The number of R combinations of a set with n elements, where n is a non-negative integer, and R is an integer with 0 less than R less than or equal to n, is C of nr. And C of nr is equal to n factorial over R factorial, also over n minus R factorial. Example 11.1. How many poker hands of 5 cards can be dealt from a standard deck of 52 cards? Solution. Because the order in which the 5 cards are dealt from a deck of 52 cards does not matter, they are C of 52 5, or 52 factorial over 5 factorial over 47 factorial, different hands of 5 cards that can be dealt. To compute the value of C52 5, first divide the numerator denominator by 47 factorial to obtain 52 times 51 times 50 times 40 times 48 to obtain, I think that's 49 times 48, to obtain 26 times 17 times 10 times 49 times 12, or 2,598,960. Example 11.2. How many ways are there to select 47 cards from a standard deck of 52 cards? Solution. Because the order in which the 47 cards are dealt from the deck of 52 cards does not matter. There are C of 52 47, which is 52 factorial over 47 factorial over 5 factorial, different ways to select 47 cards from a standard deck of 52 cards. Notice this is exactly the same as C of 52, 5. Here are some example problems. How many different permutations of the set A, B, C, D, E, F, G end with A? Solution. If we want a permutation to end with A, then we may as well forget about the A and just count the number of permutations of B, C, D, E, F, G. Each permutation of these 6 letters followed by an A will be a permutation of the desired type, and conversely. Therefore, the answer is P of 6 factorial over 6 minus 6 factorial is 6 factorial over 0 factorial is 720 over 1 is 720. How many possibilities are there for a win, place, and show for second and third positions in a horse race with 12 horses if all orders of finish are possible? We need to pick 3 horses from the 12 horses in the race, and we need to arrange them in order, first, second, and third. In order to specify the win, place, and show. Thus, there are p of 12, 3, 12 factorial over 12 minus 3 factorial, 12 factorial over 9 factorial, which is 12 times 11 times 10, which is 1320 possibilities. (11) How many bit strings of length 10 contain exactly 4 ones? Solution: to specify a bit string of length 10 that contains exactly 4 ones, we simply need to choose 4 positions that contain the ones. There are C of 10, 4, 220 ways to do that. At most 4 ones. Solution: to contain at most 4 ones means to contain 4 ones, 3 ones, 2 ones, 1 ones, 1 1, or no ones. Reasoning as in part A, we have C of 10, 4 plus C of 10, 3 plus C of 10, 2 plus C of 10, 1 plus C of 10, 0, 210 plus 120 plus 45 plus 10 plus 1, or 386 ways to do that. At least 4 ones. Solution: to contain at least 4 ones means to contain 4 ones, 5 ones, 6 ones, 7 ones, 8 ones, 9 ones, or 10 ones. We could reason as in part B, but we would have many numbers to add. A simpler approach would be simply to figure out the number of ways not to have at least 4 ones, that is, to have 3 ones, 2 ones, 1 1, or no ones, and then subtract that from 2 to the 10th, the total number of bit strings of length 10. This way we get 1024 minus 120 plus 45 plus 10 plus 1, or 848. An equal number of zeros and ones. To have an equal number of zeros and ones in this case means to have 6 ones. Well, means to have 5 ones. Therefore, the answer is C, 10, 5, or 252. 18. A coin is flipped 8 times where the flip comes up either heads or tails. How many possible outcomes are there in total? Solution: each flip can either be heads or tails, so there are 2 to the 8th, there are 256 possible outcomes. Contain exactly 3 heads. To specify the outcome that has exactly 3 heads, we simply need to choose 3 flips that came up heads. There are C of 8, 3 equal 56 such outcomes. Contain at least 3 heads. To contain at least 3 heads means to contain 3 heads, 4 heads, 5 heads, 6 heads, 7 heads, or 8 heads. Reasoning as in part B, we see there are C of 8, 3, C of 8, 4, C of 8, 5, C of 8, 6, C of 8, 7, C of 8, 8 equal 56, 70 plus 56 plus 28 plus 8 plus 1 equal 219 such outcomes. We can also subtract from 256 the number of ways to get 2 or fewer heads. Namely, 28 plus 8 plus 1 equal 37. Since 256 minus 37 equals 219, we obtain the same answer using this alternative method. Contain the same number of heads and tails. To contain an equal number of heads and tails means to have 4 heads. This answer is C of 8, 4 is equal to 7. And that concludes our lecture.